Welcome back to this course on polymer chemistry. We will continue our discussion on step growth polymerization, which we were having in last lecture. Now, let us look at what we have learned so far in terms of step growth polymerization. We have learned the mechanism of step growth polymerization and its composition over chain polymers, and we also learned how what is the effect of equal reactivity of functional group, and we also understood the justification of why the functional group of reacting molecules including the intermediate species should have same reactivity irrespective of their size and irrespective of whether the functional group present in the other direction is already reacted or not. And also we also seen that this is experimentally proven that once the length of the chain goes beyond 3 trimer, then the reactivity actually becomes independent of the chain length of the oligomeric species. We also learned the Carothers equation relating to the average degrees of polymerization and the conversion P, and we also same time learn how to get the number of average molecular weight from the average degrees of polymerization. And I gave more time in this because as I said that sometimes there are confusion among students how to get Mn from Xn. It is actually Mn is Xn multiplied by the average molecular weight of the structural unit, not the repeat unit. And we also discussed the kinetics of step polymerization, and in this class, in this lecture, what we will do, we will continue the discussion on kinetics of step polymerization and then go for predicting the number of average degrees of polymerization for a step polymerization which is happening in a closed system, and that will give us the importance of equilibrium constant of a step polymerization reaction. We then move to a step polymerization in an open and driven system where it is not possible to completely remove the condensate out of the system. That means there will be some condensate remaining in the system, polymerization system. In that case, what is the consequence of that presence of that condensate on the molecular weight of the polymer? And then we will move to the different strategies for how to control the molecular weight in the polymerization. Now, let us go back and see what we have learned in the last class in terms of kinetics of step polymerization. Now, this is the reaction we took as our model, the polyesterification reaction, and this is the reaction we followed, and finally, what we arrived at is as follows, that for self catalyzed reaction Xn bar is 1 plus Kt, where M0 is the concentration of the monomeric species at beginning, whereas for external catalyzed reaction we got Xn is 1 plus M0 K dash T. Now, from these two equation we have seen in the last class itself that it is very difficult to build a high molecular weight, high value of Xn bar for a self catalyzed reaction, and that is the reason in most cases, most industrial polymerization has taken place in presence of a catalyst which is added from outside the system. Okay. So, most of the reactions in industrial setup are carried out in external catalyzed reaction. So, in our discussion we will mainly focusing on this external catalyzed reaction, and we will not discuss too much about the self catalyzed reaction. Now, let us take a experimental observation of an external catalyzed system, one experimental observation. Let us consider a reaction adipic acid plus diethylene glycol at 190 degrees centigrade in presence of 0.4 mole % of para-toluene sulfonic acid as a catalyst, and the product is polyester plus H2O. So, this is what is observed experimentally. In this axis we have time, say in minutes, 200, 400, 600, 800 and so on, and this axis we have percentage conversion, this is 99, this is somewhere 98, and in this side we have Xn bar which is equals to 1 by T. Now, experimentally it has been found to be following something like this. Okay. Now, what do we see here in this experimental observation? We see that except this initial part, the entire region, for the entire conversion region, you have a linear relationship of average degrees of polymerization with time, which is predicted as predicted by the your reaction mechanism. Now, what does it mean? Now, remember the reaction, how did we go about the reaction? Now, during the deduction of that kinetic expression, we have used functional group like this, which means we have considered the reactivity of functional group independent of the size of the molecules, and here it found to be that expression is valid for almost entire range of conversion region, which means that this assumption what we have considered here, that equal reactivity of the functional group is valid even experimentally. So, even if at high conversion the length of the polymer chain or the oligomer chains are quite high, the reactivity of the functional group at the end of that residing at the end of the chain are same as when the conversion was smaller. That means, the size of the polymer chains are smaller. Remember, what are the other conditions we have assumed or imposed during the derivation of this expression was that there is 1:1 stoichiometric composition of the two monomer or two functional group, in this case carboxylic acid and OH, and also we are taking out this condensate, this small molecule, so that practically the reaction is irreversible. So, we are taking out the condensate small molecules H2O in this case, which to make sure that the reaction happen, this equilibrium reaction actually happens almost irreversibly. So, what are the other observations we can make here? Set for a conversion of P, for P is 0.98 or 98%, which corresponds to a Xn bar of 50, T is say around 450 minutes. Now, for P 0.99 or 99%, Xn correspond to 100 and T is almost 850. So, we see here that for reaching up to 98% conversion, it takes about 450 minutes and built a average degrees of polymerization of 50. If the average molecular of the structural units is 200, then the molecular will be about 10,000. Now, that may not be sufficient for our purpose. We are looking for building high molecular weight. For all practical purpose, we need high molecular weight. So, this 98% conversion may not be sufficient for our purpose, it will not serve our purpose. So, we must push the conversion higher to, so that the molecular weight we get is high enough for our, which will serve our purpose. So, from a 98 conversion going to 99% conversion, we have to almost double the reaction time, some 450 to 850. So, for an organic chemist which is doing esterification reaction for small molecules, a 98% conversion may be quite satisfactory, which means that at 450 minutes time he can stop the reaction and take the product which is 98% conversion, which is quite sufficient and quite satisfactory. But for a polymer chemist, that 98% conversion is not sufficient. There is no choice for a polymer chemist other than continue the reaction for almost similar time to get a high enough molecular weight, in this case Xn bar degrees of polymerization of 100. And if this molecule is not sufficient enough, then you have to keep the reaction even longer to high the conversion and hence higher the molecular weight of the polymers. Now, because you have to keep this reaction for longer time, sometimes that actually poses some difficulties in terms of stability of the ingredients, the species, chemical species which present, and as we have seen that this typically done at higher temperature, which means that if we keep this for so long a time, there is a possibility of the polymeric species might degrade and form color species which is not desired. What we also we've seen this from this equation, that Xn bar is linearly dependent on the initial monomer concentration as well, which means that to increase for a given rate constant, it is always preferred to use a high concentration of monomer, and that is why typically this reaction are done at very high concentration in solution, or in some cases they are done in a bulk. That means, you take the monomers as such, which ensures the maximum possible concentration of the monomeric unit. So, we now move to that. This again, this was deduced for a such a way that we are taking out the condensate, in this case H2O molecule. So, the reaction was almost irreversible reaction. Now, let us consider a closed system. The closed system, and take that we will write this reaction and reaction rate constant. So, equilibrium constant can be written as if the conversion is P, if the conversion at equilibrium is say Pe in this case, and M0 is the monomer concentration at the beginning at T is equal to 0, then at equilibrium what is the concentration of COH is P M0. Initially it was M0, now P M0 has reacted. So, at equilibrium the concentration of COH group is given by 1 minus Pe, and because we talking about 1:1 stoichiometry ratio here as well, this is same as the concentration of OH at equilibrium. What is the concentration of CO group and H2 at equilibrium? That is P M0. So, P M0 okay. So, that rearranging we get P as root k 1 plus root k or x n bar is 1 by 1 over P, which gives you 1 plus root k. Now, remember the difference between the earlier case and this case. In this case, we are doing or we are carrying out the reaction in a closed system, which means none of the reactants or the products are taken out from the system, and reaction is allowed to reach a equilibrium. And from this reaction, we now can say that this is the formula which relates average degrees of polymerization with the equilibrium constant. So, how this translate to the real number, let us look at this following data. These are all calculated data from this expression, and I will try to explain what does it mean in a minute. Now, if we carry out this reaction in a closed system, if the equilibrium constant K is say 1, then the equilibrium conversion would be 0.5, and which will lead to a degrees of polymerization, average degrees of polymer of 2. That means, if our reaction is such a way that your equilibrium constant is, the value of equilibrium constant is 1, then at the end of the reaction, that means at the equilibrium, you are only going to get dimers. If you want to build molecular weight, that means if you want to build say degrees of polymerization of 100 in a closed system, then your equilibrium conversion has to be 0.99, which means your K has to be almost in the order of 10 to the power 4. That means, by itself your reaction has to be very highly reactive, so that by itself without removing the byproduct you can get the product. Okay. And if you talk about a degrees of polymerization 200, say this is probably the number we look for when we make a high molecular weight polymer, then your equilibrium conversion has to be 0.995, which means your look at the number of K, value of K, which is at the order of 10 to the power 5. Okay, that means your reaction has to be very much towards the product side, reactivity has to be very high, which is seldom the case, which is not the common case. Normally, typically polyesterifications, they are of the order of 0.1 to 10, polyamidation of the order of which is probably the highest among the known typical common reaction is about of the 10 to the power 2, transesterification reaction of the order of 1 to 10. That means, typically this hang around between this. Okay. And if you do not remove your condensate or the polymer, if you wish, then your reaction will end up at a oligomer stage, maybe dimer, trimer or tetramer, it will mixture of that, but average will be say a dimer for a equilibrium constant of 1, and for equilibrium constant of 10 to the power 2 order, it will be at the stage of xn about 10. So, that gives the importance of the equilibrium constant in a reaction, in a step polymerization reaction, that you always prefer, you always better to have a reaction on your hand which is having a high equilibrium constant. So, this convinced that we have to, there is no other way, we have to do a reaction where we always continuously take out the condensate from the system. Now, what happened if we take out, the products will be moved towards right hand side. So, polymer will build, but it is not always possible, or it is almost impossible for engineering design to take out every possible condensate. No, all the 100% which condensate, in this case H2O for a polyesterification reaction, it is not possible to take out all the 100% H2O which is evolved, because of so many reasons. Because at the high, when the molecular weight build up at their high molecular weight, then the viscosity of the medium goes increases quite a lot, and when the viscosity goes up, this small molecular condensate, the diffusion of this condensate become very slow. Now, to take out that H2O molecule or any other condensate from the reaction, it has to first come to the surface, then only you can suck out that molecule from the system. But if it is forming inside the reaction, then first it has to diffuse out to the surface of your reaction medium, then only it will go off the system. So, it becomes lot of cases if the molecular weight is quite high and viscosity is very high, which is more often the case in case of bulk polymerization, that melt when you are talking about no solvent, only the monomer molecules, it is becomes very difficult. That means reactions almost becomes diffusion control. Okay. So, what we now know that it is almost difficult to take out entirely the small condensates. So, we should consider open and driven system where there is a incomplete removal of the our condensate material. So, we consider the same reaction here. In this reaction, and in this case which will come, the H2O will take out, it is taken out, but not all of them has been taken out of the system. It will be part of which or a trace of which will be remaining. So, how do we write the equilibrium constant in that case? So, for a open driven system with incomplete removal of the condensate, K again CO concentration H2O COH. So, same thing PM0. Now, in this case we do not know what is the concentration of H0 H2O. So, we are writing like this, and it is again M0 1 minus P M0 1 minus P, which makes this as now we know Xn is 1 by 1 minus P. So, this can be written as okay, let me write once again. So, what is finally K comes P okay, here we are choosing to write P instead of P equilibrium, because the true equilibrium has not been reached, because we are taking out the system. So, instead of P equilibrium in last case we are writing P as the conversion. So, let us continue with the next page. Which mean Xn now, most cases, as we learned by now, that for a high molecular weight polymer, P is close to 1. So, we can ignore this for time being for if the molecular weight is high enough. So, we can write so what does it mean? This means that the xn, the normalized molecular weight is inversely proportional to the square root of the amount of condensate present. If I make a table with the corresponding numbers, how does it look? Now, to get a, we are trying to get a xn bar of 100. How this K and H2 is related? What does this table means? The table means that if you have a reaction with high K, to build same molecular weight, in this case average degrees of polymerization of 100, we are considering average degrees of polymerization as 100. Now, to reach that level, to reach that molecular weight, if your K is higher, then you can afford to keep some of the water molecules in the system. If your K is low, then you have to make sure that you take out the water molecules as much as possible. So, to reach at level of 100 degrees of polymerization 100, you have to reach a concentration level of water molecules as low as this 10 to the minus 4 order, whereas if you have 10 to the 2 order of K, you can live with a 10 to the power minus 2 level of H2O in the system. So, again this means that if you want to build a high molecular weight, always better to take out the condensate out from the system. Now, as I said that it is not possible always to take out the entire amount of condensate from the system. So, in that case what happens? What is the next alternate way you can build high molecular weight? The alternate way is to design reactions where K will be high, because if K is high, then you can afford to keep some of the condensate molecule in the system and still build a high enough molecular weight. Okay. Now, as I said before that for engineer it is not always very easy to build a reactor where you can take out the condensate molecules to the level where you want for the building a molecular weight. So, in that case there is a limitation, there is a limit at which you can take out the condensate from the system. So, what happens if there is a limit up to which you can go down in H2O level? You have to increase, the chemist would have to design a reaction which will be inherently having high equilibrium constant. Okay. Let us take example, it will clarify more. In one of the last lectures or previous lectures, I have shown the synthesis of polycarbonate from bisphenol A using phosgene. Now, there is another way of synthesizing polycarbonate is by transesterification of bisphenol A with say diphenyl carbonate. in presence of base catalyst, base as a catalyst. So, that gives us phenol as byproduct. Now, in this reaction the phenol boiling point is 180 degree centigrade, BP of phenol is 180 degree centigrade. So, you can imagine that you have to at least have a reaction temperature of 180, so that you can take out the phenol vapor from the system. Now, the K of this reaction, equilibrium reaction, if you is around close to 1, which means that if you do this reaction in a closed system without taking out phenol from the system, you will end up in average degrees of polymer of 2. Okay. It will end up in a dimeric, it will end up in a dimeric state. So, naturally it is the reaction is done such a way that phenol is taking out from the system, and the reaction is done at very high temperature. So, the viscosity is lower and lower, so that you can take out the phenol molecule. Now, you have to increase the temperature slowly, because as you build up the molecular weight as the reaction goes, the viscosity of the medium builds. So, to take out the phenol molecule, you have to make the viscosity lower. So, you increase the temperature again, and when you increase the temperature again, the time goes up, again the molecular weight builds up. So, it is a serial process, it is a consequential process. Okay. So, here to build a molecular weight, if I consider this same as H2O case in last slide, in the last page, this K is 1. So, to build a xn of 100, the phenol concentration should be of 5.05 10 to the power minus 4 okay, moles per liter. So, you understand, because the equilibrium constant of this reaction is roughly 1, to build a molecule, a polymer having a degrees of polymerization of 100, you have to bring down the phenol level in the system to such a low level. But as I said that sometimes it is limited by the design of a reactor, it is not possible. So, the chemical engineer will come to a chemist that you design a reaction by which you can increase the K. Now, how can you do that? What is the mechanism of the reaction? The mechanism of the reaction is that you have a base catalyzed reaction. So, you have these molecules attacking to this carbonate group, nucleophilic attack, and the reaction starts from there. So, how do you increase the reactivity of this reaction? Let us see one of the strategies in the next page. Now, if we, this is the electrophilic center, if we increase the electrophilicity of this carbon, then the attack of that phenolate from the coming from the bisphenol A group will be more feasible. So, equilibrium constant will go. How it is achieved? If you increase, put a electron withdrawing group, if you put electron withdrawing group, then the attack of this, the nucleophilic attack of this phenolate ion becomes much more feasible, which will increase the K much higher compared to a diphenyl carbonate where there was no electron withdrawing group. So, in this case you can afford to keep this condensate at a much higher level compared to just phenol, which is shown that reaction equilibrium constant was 1. So, this is one example where the chemical engineers is restricted by the limitation of the reactor design, where the condensate can be taken out to a limited level, but still that will be not sufficient to build up the molecular enough molecular weight. So, in that case chemist has to design the monomer such a way that the reaction equilibrium reaction or equilibrium constant is higher. I just showed one example in this page. Now, one thing you have to also remember that to build high molecular weight, you have to make sure some other conditions. For example, you have to make sure that the functional groups are available. During the entire reaction, so that some cases what happen, these are exceptional cases where when you build a molecular weight, after some size it might precipitate from the solution or from the melt of the reaction. So, you have to make sure that all the functional groups, that means all the monomeric species or the oligomeric species, they stay in the solution or in the reaction medium all the time during the reaction. And you also, there are some exceptional cases that this equal reactivity of the functional group does not apply, but those are, we are not talking about those cases in this course, because they are exceptional cases, and most of the all those common reactions and the reactions we come across always are follow this rule of equal reactivity of the functional groups. So, we move to the next topic. How do you control the molecular weight? So, strategies for controlling the in a step polymerization. Now, why do we need to control a molecular weight of a step polymer? Now, if you say I am targeting a molecular weight of something which corresponds to a average degrees of polymerization of 100. Now, if we will end up at the end of the reaction something higher than 100, then also problem. If we will end up a number which is lower than 100, then also a problem. If it is lower, then the polymer will not be serving our purpose, and if it is higher, then it will pose lot of other problem, like taking the polymer and processing for the application will be difficult, because the melt viscosity of this polymer is higher. So, handling will be difficult. This is one example of the difficulties if you have higher molecular weight than the targeted one. So, it is always desirable to have your reaction stopped, or at the end of the reaction you get whatever you targeted for. So, you target for 100, it is always desirable that at the end of the reaction you should get average degrees of polymerization of 100. Now, how do you do that? Now, we have seen that xn of 100 corresponds to a P of 0.99, a 1:1 case, okay, 1 is stoichiometric ratio of the functional group. So, you can say that if I stop the reaction, and we know this reaction kinetics, how the P varies with time, we also know how P is related to time, we have seen in the previous pages. So, you can always say that if you stop the reaction such a time which corresponds to a P of 0.99, then we will get a molecular weight of corresponding to degrees of polymerization of 100. So, as simple as that. But what is the problem in that? Now, if you stop a reaction at a level of say 0.99 or 99% conversion, what do you get in hand? So, if you are talking about a polyesterification reaction, what you get at 99% conversion level? You get average of 100 and what you have both the sides and you also may have some monomer present. So, at the level of 100 degrees of polymer 100, what you have in this reaction medium? You have the hydroxy acids, okay, which corresponds to some size, and you may also have, will also have some unreacted monomers as well. So, if you do the reaction in or stop the reaction in this level, what you have? You have till the possibility of these molecules participating in the further reaction. So, when you take this polymer at this stage and mix with the other additives and fillers and do a compounding, which is a further process which you do in a melt stage, as I said in the first lecture, then these functional groups are free to react at there. So, they might do react and build molecular weight, or they might bite in between and degrade the molecular weight. So, if you stop a reaction to build a molecular weight or target a molecular weight of 100 degrees of polymer correspond to 100, if you stop a reaction at 99% conversion level, starting from 1:1 stoichiometry ratio, you get this, but this will pose lot of difficulties in the next step when you do processing step like compounding or molding, because this has presence of active functional groups. So, this can react with each other or a polymer backbone and degrade the polymer or build the molecule. So, you know at the end of your molding step, the molecular weight might be different than what you targeted for. So, your properties what you targeted will be different. So, it is not advisable that you do a reaction and stop in between at the level what you targeted for. So, how can we achieve that? What is the strategies we can achieve what we targeted? One is to use one of the monomers in excess. For example, say you have a monomer A and BB. Now, take concrete example of a polyamide formation. If I take this, if I take this as excess, now this will react with this acid functionality as long they are present, because they are present in a smaller amount. At the end, all this carboxylic group will be consumed and you will end up a polymer or oligomer chain with both sides amine groups. So, you will end up something like this. So, in this case both the sides are amine group. Now, these cannot react by themselves. So, if you stop the reaction in that level, now you are ensuring that there is no leftover COH group, carboxylic group in the medium, so that they cannot take the amines by itself cannot take part the reaction themselves. So, if I take the excess the carboxylic group, what will end up in? You will end up in something where both sides have COH group, right. So, if you have excess this diamine as a excess quantity, then you will end up in a polymeric or oligomeric chain where both sides are capped with amine group. If you have excess dicarboxylic acid, then you will end up in the polymeric oligomeric chain having dicarboxylic acid, carboxylic acids at both the ends. So, which will ensure that these cannot react by themselves. So, that your polymers are virtually dead, unless you have something in the reaction medium further. When you take these polymers out and do a compounding and molding step, unless you have something in you are adding from outside which will be able to react with either of these leftover functional group, then it will stay as it is. It will not react with the functional group present in the polymers formed itself. Okay. So, that is one of the strategy of making or controlling the polymer, as we will see how what is the quantification, how much excess you have to take to target a certain molecular weight. We will come to that quantification level in next page. The another strategy is to take a chain stopper. Chain stopper molecules are molecules having monofunctional group. So, instead of taking A plus BB, you take just B in excess. Then the chain in which the ends are capped with B, the other ends are dead. This is dead end. So, if you have some chain like this, B with dead end here and again B with dead end here, then you are forming a chain which does not have a reactive group in either of the sides. That means, this reaction, this monomer cannot, or this chain cannot take for further reactions, which will allow you to control the molecular weight. Let us take an example. If I take a, again go back to same polyamide formation. If I add a benzoic acid, you are going to get a molecule something like this, some molecules. Okay, so, this ends does not have any reactive functional group. So, by this way, if you have all the chains are capped with a non-functional entity, not reactive group, then will this these molecules will not take part for the reaction. So, if you take this out, this polymer out and do further molding and compounding, go to the compounding step, then because these chains are capped with a non-reactive group, they will not take part for the reaction, which means your polymers are practically dead polymers. So, your molecular weight not change. So, whatever at the end of your processing steps, you will get the same polymer, the property which was related to the molecular weight of your target molecular weight. So, you will get that same property, because but in the first case, if you stop the reaction in between at some conversion level, then what happened in after step, you go through the compounding and processing step, and the final article, final application, the molecular weight will vary from your target molecular weight. That means, the properties also will vary. Okay. So, it is advisable, it is always done, and industrially also it is done by either by taking one of the bifunctional or polyfunctional monomers in excess, or a monofunctional monomer which is termed as chain stopper added externally, so that we can control the chain length target. Now, what is the how we can relate to the amount of excess or amount of this monofunctional chain stopper, how they related with the target degrees of polymerization, we will come to the next class, next lecture, but in detail. But just to before we go to that quantification, how did we get the xn bar for any polymer mixture? Remember, it is the number of molecules at the beginning and number of molecules at the end. So, which will give you the average degrees of polymerization. Okay. So, what we will do, we will take from this and continue in next lecture the quantification. That means, we know that there are two strategies we can follow. We can follow taking one of the bifunctional monomer in excess, or we can add some amount of chain stopper, which are nothing but monofunctional groups. But how much excess should I take? What is the relation between conversion and excess and the molecular weight? How much should I take? Because excess, if you take too much excess, then ultimately you will not land up in the target molecular weight. The molecular weights will be even it could be very low. So, you should know a priori what is the relations between a molecular weight and this the ratio between the monomers bifunctional, or if we add, what is the effect of molecular weight if we add some monofunctional group from outside. We will come back to in the next lecture with that